It is a
Okay.
panel, but with
Okay.
Craig
I was looking for the right now.
Yeah, panel works.
It's a panel. It's a panel. It's a panel. Maybe we'll find life on Mars while I'm gone. You never know.
Well,
Yes, that'd be sweet.
I would
fun,
that
yeah.
for you, but
Yes.
anytime.
I'll take one for the team. Yeah. It'll be
Right.
much anticipated.
So,
I think my husband's going to take off
Yeah.
through New Year's, hopefully.
Gareth Morgan, pleased to meet you. How are you doing? Of course, yeah, lovely to be here. I can get up and tell a funny story. It's related to Mars and what we're talking about. Should I?
Okay.
yeah, it'd be great.
Is this thing on?
My only challenge is
We're improvising here for a second because there's a technical difficulty, so we're going to actually start with the panel in a moment. But since we had just a minute and we need to fill the time, I thought I'd tell you a story that I find
the
amusing.
way my calendar works. other than-
And it involves another panel about Mars, and this was at a meeting I was at, I guess about 15 years ago. It was one of the early astrobiology science conferences, and I was on a panel that was about the possibility of Mars terraforming. And one cool thing about the panel was that one of the panel members was Arthur C. Clarke. But Sir Arthur was not there in person. He was participating by satellite from Sri Lanka, where he lived. And that was also kind of cool because Arthur C. Clarke is the person who invented the concept of the communication satellite. So it seemed fitting to have him by satellite on our panel. Except, this is what reminded me of this because we're having a little bit of internet technical difficulties now. Except, of course, this was early days of that kind of technical facility. And of course, it didn't work. It would have been great if it did work. But we almost got none of Sir Arthur in that panel because the connection was bad. Except there was one point where the signal faded in for about 20 seconds, and we got to hear Arthur C. Clarke's opinion on this topic, which was the terraforming of Mars. And so he said one thing, and it was, well, I think we should ask the Martians first. That's my story. Thank you.
Well, thank you for your patience. I think we're ready to get started. Hello and welcome. My name is Paul Steimers. I'm a partner here at K&L Gates. For those of you who may not be aware, we're a large global law firm and lobbying firm. I'm in our public policy group with a practice mostly in innovation and in particular in commercial spaceflight. So it's a real pleasure to be involved with the Museum of Science Fiction. I'm on their advisory board, and to be able to host events like this, our lecture series. I should say our next lecture, which hopefully you all got a press release for, is November 8th. It's going to be on the Space Force. Todd Erickson, the director of the Aerospace Security Project at CSIS, will be here to talk about what the Space Force really is going to be all about, or what it should be about, as opposed to what it's been made out to be by all sorts of crazy people on the internet. So we're looking forward to that as well. And then, of course, I hope you'll all come to Escape Velocity, the annual event this coming Memorial Day weekend at the Gaylord Hotel just across the river. It's bigger and better every year. This year they've got. I'll let Mandy and Greg tell you a little bit about what's coming, but there's some really fun stuff that's going to be there. So again, thank you all for coming. I appreciate you all being here. This is the biggest crowd we've had so far for one of these, and hope you all come back soon. I'd like to introduce Mandy Sweeney, who's the head of operations for the museum, to introduce our speakers. Thank you very much.
Good evening, everyone, and thank you, Paul, for yet again hosting us here at this beautiful location. We always love to come here to K&L Gates, and it is great to see so many people in the audience tonight. When we founded the museum 4 years ago, it was 5 years ago now, we had this dream of creating a center of gravity for science and imagination, and it's our mission to use science fiction as a way to inspire and engage positive thoughts about the future, education, and possibility. So I'm glad that you're here to be a part of that. Paul mentioned Escape Velocity, which is a 3-day convention that will be over Memorial Day weekend. We have over 300 hours of interesting programming, much like what you'll see tonight, but also a lot of things for families and kids and workshops, and lots of different ways to get involved and really become a stitch in the fabric of our mission. So I hope that you'll join us. Now, I have the challenge of introducing our moderator tonight, Dr. David Grinspoon, whose achievements are so numerous that if I did not pre-print the approved paraphrased version of his biography, I would be up here rambling for days. So forgive me for reading a little bit, but it's really the best way to make sure I don't ramble on and on. So Dr. Grinspoon is an astrobiologist. He's an award-winning science communicator, a prize-winning author, and a frequent advisor to NASA on topics of exploration. Dr. Grinspoon is a senior scientist at the Planetary Science Institute. In 2013, he was appointed the chair of astrobiology at the U.S. Library of Congress, where he studied the human impact on Earth and organized a symposium on the longevity of human civilization. He lectures widely. He may be familiar to you from his many appearances on television, radio, and podcasts. So welcome, David. Thank you for being here, and I can't wait to hear your presentation. Thank you.
Well, thank you very much, and thank you all for coming out. And what an appropriate venue, the Museum of Science Fiction. Mars has always been such a stimulus to our imagination, and the science and the science fiction have fed off each other and have evolved over time as we've learned more, which has allowed us to imagine more, which has inspired explorers to learn more. So there's been this sort of fun feedback between the science and the imaginative process. This is thrilling to me tonight because it's such an exciting time in the exploration of Mars, and I have these wonderful, brilliant panelists to share what they know, and then we'll each give a brief presentation, and then we will have a panel and open it up to hearing what you guys have to say and answering questions as well. I think what I'll do, actually, before I give you my little spiel, I'll introduce my fellow panelists now, tell you who they are, so that then we can all just sort of proceed and give our presentations and get on with the conversation. So I'm going to basically, for a few minutes, give a little bit of historical background and some of the sort of back and forth ideas about Mars and life and how those ideas have changed a little bit historically with new missions and new discoveries. And then the panelists here will fill you in on some more recent and current and ongoing and even future missions and discoveries. So after I do my spiel, in a way, the reason why we're here now, or the discovery that catalyzed the idea of having this discussion right now, is something you probably heard of, which was the very recent and exciting discovery of ice-covered lakes under the polar caps of Mars. And after me, Dr. Gareth Morgan will speak specifically about that discovery and tell you how it was made and if it's real, if we can be confident it's real, and what it might mean. And so Gareth Morgan, sitting right here to my right, is a research scientist at the Planetary Science Institute. He specializes in conceptualizing complex ideas and research results to peers within the science community as well as with the public. And he's been awarded a number of grants from NASA and is on the trail of the question of life on Mars. He holds a PhD in geological sciences from Brown University, a fine institution, my undergraduate alma mater. I approve. And after Gareth, we're going to hear from Dr. Jennifer Stern. She is going to tell us about this other fantastic ongoing mission, which, of course, is the Curiosity rover and the Mars Science Lab, which she is involved with. Jennifer's a space scientist at NASA Goddard Space Flight Center right up here in Greenbelt, Maryland. And her specialty is geochemistry and astrobiology, but she also works on developing the actual instruments used to explore Mars, including on the Mars Science Laboratory and Curiosity. She also participates in field experiments to unlock secrets about Mars that may be recorded here on Earth in the rock record. She holds a PhD in geochemistry from Florida State University. And then after Jennifer, our last panelist to speak will be Dr. Michael Meyer. And Michael has the very cool title of being the lead scientist for NASA's Mars Exploration Program at NASA headquarters here in Washington, D.C. Previously, he's worked as a NASA senior scientist for astrobiology and program scientist for the 2001 Mars Odyssey mission. Michael holds both master's and doctorate degrees in oceanography from Texas A&M University, and his past research has emphasized microorganisms living in extreme environments, and that's a topic that's sure to come up tonight. And Michael will also be telling us about some plans for future missions and how we're, assuming we don't answer all the questions tonight, how we're going to address them in the future. So that's who you're going to hear from. And now let me just talk a little bit about Mars. And Mars has always kind of got under our skin. I mean, human beings have been fascinated with all the planets since that time long ago. We realized that they were different from the stars because they wandered about in the heavens. They didn't stay put. That's why the word planet is really a word for wanderer. But Mars in particular has always been an object. It's not even really an object anymore, a place, almost a persona of particular interest. And I think part of the reason for that is because certainly since the age of the telescope began 400 years ago, you can see Mars changing, even with a backyard telescope. You can see these features on Mars, these dark areas, and the polar caps changing over time. You can see the seasons coming and going, the polar caps growing and shrinking, and these dark areas that come and go with the seasons. And people have noticed this for a long time. There's something kind of animated and kinetic about Mars, which seems alive. Whether or not it is alive is something we're going to be discussing tonight, but it certainly has that sense that it's not static. And I think that's been part of the source of human imagination. It's also its behavior in the night sky is sort of, it has a personality. It's big and bright and red, and it's zooming night after night in one direction, and then all of a sudden when it's near its brightest, it backs up and goes in the other direction, which is called retrograde, which is what happens when Earth is passing Mars in its orbit. It looks as though it backs up and goes forward for a while. So it has this almost kind of playful trickster aspect to its motion that I think is the source of some of the mythology. And then, of course, it's blood red color. It probably has been interpreted as, the source of it being the god of war and all that. For whatever reason, Mars is, even before we were able to go there with spacecraft and learn so much about it, has always been a place that has stimulated the human imagination. Well, a big watershed, so to speak, in our ideas about Mars, a big stimulus to the imagination, happened about 100 years ago now, a little more, with the work of this gentleman, Percival Lowell, who was a Bostonian gentleman astronomer who became very enamored of certain ideas about Mars and life on Mars. And he was a very charismatic and persuasive writer and speaker, best-selling author. His lectures, overflow capacity on his lecture tours. He was sort of a Carl Sagan of his day, and he was the discoverer, of course, of the canals of Mars. That, now we know were sort of an optical illusion born of the fact that people were trying to infer things beyond the resolution of their telescopes. But at the time, he was so persuasive that he really had the world for a while believing that there were canals on Mars, and he had this whole interpretation that it had to do with a dying civilization that was, actually suffering from climate change, and the planet was drying up, and so they had this network of plumbing, of irrigation to channel water from the polar caps to grow crops at lower latitudes. And he was very persuasive, and a lot of people believed it for a long time. And then, of course, when we got better telescopes and photographic plates attached to those better telescopes, it became really incontrovertible and obvious that there were no canals on Mars. And then there was sort of a backlash against some of these ideas about life on Mars. And it was sort of discredited for a while. But, it's the kind of idea that it can't be killed for long. And it's an interesting question that maybe we'll come back to in this panel here. There's this sort of irrepressible optimism about the possibility of life on Mars that, maybe is a valid intuition, or maybe clouds are thinking. but there's a sort of wishful thinking aspect to it that returns time and again. Turning to science fiction for a second, H.G. Wells was not just one of the first really great science fiction authors. He was also a man of science, and he read up. He was very familiar with Lowell's ideas, and War of the Worlds was in part based on Lowell's. It was basically Lowell's view of Mars, but also he was very moved by the story of the indigenous Tasmanian population being completely wiped out by European intervention, and that those two stories of colonial destruction and of Lowell's Mars were basically, he combined those in War of the Worlds, which is sort of an indelible part now of the way we think about Mars. And he sort of invented the trope of invading aliens, which has come back time and time again in science fiction. And War of the Worlds is a great book. I mean, just that opening paragraph, I won't try to quote it from memory, but about mind is superior to our own watching the Earth. I mean, it's just like and there are a lot of great passages in that book that reflect the science of the day. So it's always worth going back and rereading. And of course, then a few years later, a couple decades later, Orson Welles, actually Halloween 1938, did his radio play of War of the Worlds that was based on H.G. Wells's book. And of course, but in this in his version, the aliens were in New Jersey, and he made that radio play so realistic that it freaked a lot of people out, and now is also kind of an iconic example of how sort of fear and belief in alien life can sort of go viral way before there was an internet. The power of mass communication, as evidenced by Orson Welles, really, people realized, hey, you really shouldn't. Even though it makes for good theater, you probably shouldn't pretend on the radio that we've been invaded by Martians, because some people are going to end up in the emergency room, which did happen. Anyways, there was Mars fever through much of the early 20th century as a result, largely of Lowell's ideas propagating. And here is just one random example: the Signal from Mars March and Two-Step, a popular piece of music from, I think the 1930s. And, there's just obviously so much very rich and a just fantastic treasure house of Martian lore that came out of these discoveries and the response to these discoveries. Well, the scientific community, sorry about that if you can't read this that well, it's a little wordy, but I'll basically tell you what it says. The scientific community was pretty optimistic about the idea of life on Mars right up to the beginning, right before the space age. There was a general idea that Mars was pretty Earth-like, probably. It turned out that when we explored it, it wasn't as Earth-like as a lot of scientists thought. And in case you don't have a 2040 vision, I'll tell you that the first of these is a quote from a report in Science magazine in 1957, so mainstream scientific discovery, where an astronomer named William Sinton reported the discovery of chlorophyll on Mars. And he said, this evidence, together with the strong evidence given by the seasonal changes, makes it seem extremely likely that plant life exists on Mars. And in 1959, so this same period, right, very beginning of the space age, Harold Urey and Stanley Miller, very famous chemists who were very instrumental in some of the early chemistry that led to our understanding of the origin of life, argued in Science that both Mars and Venus should have conditions suitable for life, and that their primordial environments on those worlds should have been similar to that which gave rise to life on Earth. So there was a scientific optimism when we first started exploring. Well, that was shattered a little bit by the very earliest missions. Mariner 4 flew by Mars on July 14th, 1965, the first flyby of Mars, and it did not show forests or swamps or anything that seemed very friendly to life as we know it. It showed craters and not much else. And here's the New York Times article by Walter Sullivan, who was a very, was sort of the science reporter of his day. And he's going to come back into our story in a minute. But he was the reporter that always wrote about these things for the New York Times. And the beginning of this article says that a heavy, perhaps fatal blow was delivered today to the possibility that there is or once was life on Mars. The Mariner 4 photographs show a crater-pocked landscape lacking any sign that there has been water erosion there. There is no evidence of river valleys or ocean basins. Basically, virtually all theories for the origin of life demand the presence of liquid water, preferably in large quantities. Basically, he's saying, now that we've seen what Mars looks like, sorry, there's just no life there. End of story. And the idea of life on Mars became sort of a subject of mockery. In the editorial in Science magazine, the editor of Science said, in looking for life on Mars, we could establish for ourselves the reputation of being the greatest Simple Simons of all time. So there was the opinion that NASA should not spend any more money on this enterprise. But of course, curiosity is unstoppable. And fortunately, there were a lot of people that wanted to keep going. The first time we were able to send an orbiter to Mars, it was a mission called Mariner 9, and it orbited Mars in 1971. And Mariner 9 was a huge breakthrough because the problem with a flyby, like the first Mars missions, Mariner 4, you get a little glimpse of one spot on the planet, and then you're inferring everything about that planet from that one spot. Well, think about trying to do that with the Earth. Earth is such a diverse planet. If you just were going to look at one spot, well, it would probably be somewhere in the ocean. And you'd say, well, that's cool, it's got oceans, but it's just, that's all there is. Or, you'd be in the Sahara Desert, and you say, well, it's a desert planet, that's all. But you've really, a complex, interesting planet you can't characterize with a flyby that shows you one spot. And we really learned that with Mariner 9 because so much was revealed, and Mars turns out to have giant volcanoes and giant canyons, and indeed, dried up riverbeds and dried up channels, and lots of evidence for at least ancient water on Mars. So if that inference that was made in the New York Times in 1965, that you need water for life, if that is correct, then you have to be able to argue the other way, that a planet that shows evidence for having had water could be a place where you could have had life. And indeed, Mariner 9 reopened that for us. And there was a wonderful panel that I wanted to mention in 1971, right after Mariner 9 returned some of its early results. It was a panel that was held in Southern California, in Pasadena, near the Jet Propulsion Laboratory, where a lot of these missions have been run. And it was called Mars and the Mind of Man. Well, this was 1971, and I think today we would use slightly different language, which is why I called in my opening slide, I said Mars and the Human Imagination, because we don't, most of us don't use the word man in that generic sense anymore. And we also try generally to avoid, or more and more we're avoiding having all male panels, because, well, this is the 21st century, folks. Anyways, but be that as it may, this is a very cool book, and it reflects the thought and the culture at that time. And the panelists, what happened was that they'd had a panel and they exchanged ideas, and it was a group of scientists involved in the exploration of Mars and science fiction writers, which was a great combination. And this book has the transcript of their conversation. And then each of them was asked a year later to write an essay reflecting upon it. And the book came out in 1972, and it has the transcript of that initial conversation plus the essays they wrote. And it's really terrific. I loved this book when I was a teenager, and it was fun to sort of recently rediscover it. So here are the panelists that I mentioned. Walter Sullivan, the New York Times writer, he moderated it, and the science fiction writers were Arthur C. Clarke and Ray Bradbury, and the scientists were Carl Sagan and Bruce Murray, both you've heard about Sagan, and Clarke. Good point. Yes. Although he was there in his capacity as a science fiction writer, but you're right. Well, I mean, Sagan wrote science fiction too. So the lines are blurry for a reason. But I know you know who Sagan is. You may know who Bruce Murray is. He and Sagan together founded the Planetary Society, and he was a very distinguished and prime mover in planetary geology. And what's fascinating about reading this transcript is, well, for one thing, I got a couple quotes here. Ray Bradbury said, this is a quote from him at the panel, "At this moment in history, it looks as if I must semi-retire to the wings and hope it becomes part of some strange new mythology. This is probably true of many science fiction authors this week." In other words, now that we're going to Mars, our stories are obsolete, is kind of what he was saying. Of course, since then it's generated all kinds of great news stories. But what's really cool to me in reading this is that Sagan and Murray, for one thing, they vehemently disagreed with each other in a very civil way. And it's kind of nice in this day and age to realize that people can be very friendly and civil and constructively have very different views and share them. But more to the point, it's kind of a time capsule of scientific thinking, because Sagan and Murray both had strong interpretations of what Mariner 9 was seeing, and they were they disagreed with each other. And what's interesting to me is they were both completely wrong. I mean, given what we know now, and who knows, I mean, they were both really smart, and, everything we tell you tonight, if anybody looks at this recording in 50 years, they'll probably say, oh boy, those guys were all wrong. So I'm not saying in any sense that we're superior intellects, but given what we've learned now about Mars, so Sagan's view, Sagan was the perennial optimist about life on Mars. And his view was, he said, well, so we don't see forests and, we haven't found any organisms or cities, but he felt as though Mars was in a state that oscillated between more Earth-like conditions and more sort of dry, cold conditions like Mars is now. And his assessment was that there was enough water and carbon dioxide locked up in the polar caps so that when Mars went through climate change, and we know it does go through climate change, that it would periodically have as thick an atmosphere as the Earth. And that in those times of warm, wet, Mars would episodically become warm and wet, and there could be organisms that that went into a sort of dormant stage as like spores, and then came alive again during those warm climate episodes. And this was a very common view of Mars that Sagan propagated. Now we know it's not true. Mars does go through climate change, but there is not enough water and carbon dioxide in the poles so that Mars can become Earth-like every once in a while. It may have been a long time ago in the past, but it's not. It doesn't have that potential now. And Murray, what he said was, "Oh, Carl, you're way too optimistic about life. That's clearly wrong." But his view was that Mars had its potential in the future, that it was just coming to life geologically, and that in the future it would be more and more Earth-like. And he interpreted what he was seeing in the Viking images to say, oh, well, we can see incipient plate tectonics, and Mars is just ramping up. And that, of course, is completely wrong, too, based on what we know about Mars. And so it's just really interesting to see these two brilliant guys arguing. And actually, well, the voice from the future, actually, you're both wrong. But there's one quote that I love here, and I wish I could really say it in a Sagan-esque voice, which I can't, but that Murray was criticizing Sagan's optimism and saying, you're blinded by, your interpretations are blinded by your optimism. And Sagan countered, "Because a possibility is interesting, it doesn't follow that it's false. We can be emotionally predisposed as pessimists as well as optimists." I know that wasn't a very good imitation, but at least I did the deep baritone, right? Okay, so anyways, so it's fun reading about that now. Moving on, the next mission was Viking in 1976, the first landers on Mars. And this largely motivated by Sagan's vision. It wasn't just him, but he was a very persuasive proponent that Mars could have these Earth-like organisms sort of lying in wait for water. The Viking biology experiments essentially tested for Earth-like organisms that, if you squirted some water and some other nutrients, would come to life. It's a little more sophisticated than that, but that was basically what they did. And now we regard those Viking biology experiments as kind of naive. It's not really the best way to look for life. But on the other hand, Viking was a hugely successful mission that taught us so much about Mars in so many ways. And maybe the Viking biology search was something we sort of had to go through in order to become more sophisticated in the way we think about life on Mars. And we're going to hear a little bit more tonight about more modern approaches. But Viking was, I was a teenager when it landed, and it blew my mind. We're landing on Mars, and as an undergraduate, I got to work. One of my first jobs was working on the geology of on the Viking images of the surface of Mars, and it was, a tremendously successful mission in so many ways, except for, well, we didn't find life. Post-Viking, there was a downturn in optimism, or uptick in pessimism about life on Mars again. And one of the lead investigators, Norman Horowitz, wrote a book. One of the lead investigators of the biology experiments wrote a book in which he said, "The failure to find life on Mars was a disappointment, but it was also a revelation. Since Mars offered by far the most promising habitat for extraterrestrial life in the solar system, it is now virtually certain that Earth is the only life-bearing planet in our region of the galaxy. We have awakened from a dream." Well, we didn't stay awake that long, or we started to dream again. But the fact is, since Viking, we've had all kinds, and I'm going to wrap up here because I want time for our other speakers, but we've made many discoveries that encourage us still to think about life on Mars. Certainly the past of Mars, we now know, was a watery time, not just for a brief period, but for a prolonged period in which these kind of layered deposits got laid down in varying climates, but a lot of evidence of water in these sedimentary rocks. And just this one sequence of images, you can see, if you look in this one square, and then I'm going to blow it up, you can see there's a And basically, there's a river delta, a dried up river delta, where some stream has flowed into a lake and fanned out. And then if you look at that one square there, and I'm going to blow it up again, you can see there's a river that's meandered. And rivers don't meander in a day. This is the result of prolonged fluid flow over, I'm not sure exactly how many years, but it did not occur in a day. Probably decades or centuries are represented here. So there's a lot of this evidence. And then the global topography of Mars, this area in the north is interpreted as an ocean by a lot of people, an ancient ocean bed. And then there are these features that are called recurring slope lineae, which are places where that come and go, where it seems as though something is flowing downhill, and those might be temporary springs of water. And then, of course, in the early 1990s, in the early 2000s, 2004, was it 2004? The Mars exploration rovers landed and rolled off and started scratching and sniffing the rocks. And the second one, the Opportunity rover, fortunately landed right by these rocks, which are sedimentary rocks that contain minerals. There's one mineral called jarosite. It's a sulfur-containing mineral that, as far as we know, is only laid down in the presence of liquid water. So this was the ground truth, that picture we were getting from orbit of a planet with a watery past was very much true. Even when you went to the surface, you could find that evidence. I'm going to skip ahead now because I really want to let the other panelists speak. But the last thing I'll say is we have not got a picture like this yet, where Marvin the Martian peers into the camera and says hi. So we're still on the trail of life on Mars. And we'll come back and have more discussion about how close we may be, or whether that prospect is good or isn't. But right now, I want to open the floor up and let Gareth give his presentation. So, Gareth Morgan.
Well, good evening, everyone. It's really great to be here. So I'm going to be talking more specifically about that recent discovery of a potential lake on Mars. And so I want to go through the rationale behind searching for lakes on Mars and explain how radar can help us achieve that goal. So following on really from what David was saying, of course, Mars is an Earth-like planet. That's why it's so compelling. That's why we think there could be life, maybe life in the past. One of the striking features to me is not so much just the similarities in terms of like volcanoes or canyons. It's the fact, as David said, if you go into a good telescope in the backyard, you'll see polar caps on Mars, just like the Earth has polar caps. And here we have a Hubble Space Telescope image. And you can see in the bottom part of the globe there, you've got the southern polar cap of Mars. And so if we take a closer look, of course, there's two of them, just like the Earth. Here you can see the panel on the top. That's the north polar cap of Mars. That image is about 1,000 kilometers across. And then the one below it is the southern polar cap to the same scale. And the sort of what you're seeing there in the white is ices. In the north, it's largely H2O, water ice. And in the south, it's CO2. But that's only part of the picture. And if we kind of zoom out, I'm going to show you now a computer-generated sort of view of the southern hemisphere of Mars, but it's using real topographic data. Here you can see the southern polar cap there in white. But surrounding it is these very smooth and gigantic deposits. They're dusty on the surface, but what they comprise of largely is actual H2O water ice. And in some areas they're over a mile thick, 1,000 kilometers across. And you have similar scale one in the northern hemisphere. And what's really compelling is that these deposits, to some extent, are in communication with the current atmosphere in terms of exchanging water. And so what you have is a hydrological cycle on Mars, just like you have a hydrological cycle, on the Earth. Of course, on Mars, because the pressure's so low, the atmospheric pressure, if you put glass of water on the surface, it would just boil away. So unfortunately, most of the water seems to be either in the solid phase, or then in the gaseous phase. Whereas, of course, on Earth, a lot of the time, water spends its time as water, as liquid. I mean, the surface is literally drenched in water. Of course, water is very important for life, and so we've always been trying to find evidence that. We know in the past there was water on the surface. In fact, the Curiosity rover was currently driving around now on an ancient lake bed. But what about the present? It'd be really neat, obviously, to find water and be really good, strong argument that there could still be some sort of life, if ever it existed, on Mars today. So there was, a few years ago, there's a discovery by the HiRISE cameras showing these sort of dark streaks that appear seasonally on the surface, and it was hypothesized that maybe these are liquid water that's melting. But most recently, this is what I'm going to be talking about today, is the potential of an actual lake on Mars. It's really exciting, quite a large body of water. So where is the lake? Well, the reason I put this image up is the lake is right here underneath the South Polar Cap. Now you might be like, hang on, Mars is cold enough. What is a lake doing at the bottom of a mile thick load of water ice covered in dry ice? It seems like kind of a strange place to have it. Well, there's some precedence to this. And if we look at the Earth, in fact, our southern hemisphere of the Earth got Antarctica, the largest extent of ice we have on the planet. It's actually kind of riddled with lakes at its bed. Now, for those of you who've been to, say, places like Montana, seen Glacier National Park, or maybe gone over to Iceland, you might be like, well, I've seen glaciers and there's water pouring out of them. Well, those are temperate glaciers and they're wet based. When you go to areas of the super high latitudes like Antarctica or Greenland, there the ice is what's called cold-based glaciation. So what happens there is the ice is actually frozen solid to the rock below it, and it flows by internal deformation. And so we weren't expecting to see any water below these, just because it's super cold. But from the 60s onwards, you started discovering them. And one of the most famous ones was indeed Lake Vostok, which is highlighted there, which is similar sort of volume and scale and sort of rivals some of the large lakes we have here in North America. And not only that, but it seemed that for continual research on this, there's actually looks like there's connections between these lakes. And periodically, it highlights here on this NSF slide as rivers, maybe a bit of a stretch, but certainly there's this internal plumbing at the base of these ice sheets in which water can communicate from one to the other. And this is a photograph I took. I do occasionally some work in Antarctica, some Mars-related work. And so this is a photograph I took from a helicopter looking up to the East Antarctic ice sheet is there in the far distance. What we can see in front of you is the Wright Valley in front of you there. And then behind that, before the sort of glacial tongue, there's kind of this hummocky terrain of isolated mesas. And this is called a labyrinth. What these are is flood channels that are carved out when periodically some of the water from underneath the ice sheet comes pouring out, and to use the Icelandic term, a jökulhlaup, which just basically means glacial flood, comes out and ends up into the ocean. So it's incredibly complicated plumbing system here that we're only now beginning to understand. So how do you get water below kilometers thick of ice? Well, one thing on Mars was saying about it, if you had water on the surface, it would just instantly evaporate into the atmosphere because of low pressure. Got the other situation here underneath these kilometer thicks of ice. This huge amount of mass pressing down can actually be enough that allows water to be liquid below the freezing point that we're used to, below 0 degrees Celsius. And so as a result, you can have water forming in those conditions. Another means, which is actually more probably apparent to Mars, is the potential for inclusion of salts. Obviously, if you put salts down your path to melt the ice every winter, and it decreases the melting point. And actually, in this image here, right where it says Antarctica, that is a small pond there. It's called Don Juan Pond. It's the most saline water body on Earth. 18 times as salty as the ocean water, and that body, for instance, it stays liquid right through the Antarctic winter, where you'd have almost 6 months of no at all. So you put a lot of salt in, you can also get water as well in areas where you wouldn't expect it. So even if we go to Antarctica, of course, it's Earth, it's not Mars. We can actually get there. There are bases there. Many countries have that. It's still tricky finding lakes at such great depth. You can drill down, but it's an expensive project, so you can't just go drilling, willy-nilly hoping to find a lake. So just on Earth, and just as I'll talk about on Mars, what we employ is geophysical techniques, and particularly the use of radar. I'm sure a lot of you are familiar with radar, has multiple applications. Basically, a radar system consists of two components. The first is a transmitter. It emits a pulse of electromagnetic radiation, typically wavelengths between millimeters to tens of meters or hundreds of feet. And then that goes out, and then it hits a target that we're interested in, bounces off the target, and comes back. And then you have a receiver, and that picks up the target. Now, picks up the returned echo, and from that you can tell a lot of information. So here in this cartoon, you can see a radar trying to search for a plane, and so you can see how long it took the signal to come back. That'll tell us how far the plane is away from the radar. You can use a Doppler shift to work out how fast it was going, and you can also find lots of other information about what the plane is as well. Whether you differentiate a plane from, say, an intercontinental ballistic missile, and indeed, the first application of radar was for military reasons. Here in the panel, you can see the initial development of radar during World War II to defend UK from German air attacks, and basically this was a early warning radar. Of course, they're still employed today. But there's also a lot of applications to geophysics and planetary. And so there on the right is the Chinese Chang'e 3 mission, landed on the moon rover a few years ago, and it employed a radar, ground-penetrating radar. And so the idea then is it sends radar into the ground, and you're not looking for a moving target such as a plane, like I showed in the cartoon, but instead you're looking for subsurface structure. And in a case of Chang'e 3, it was looking at lava flows embedded on top of each other, buried below the surface of the moon. And then when you get the reflections back, you can get an idea of how deep. You can time how long it took the echoes to come back and get an idea of how deep these are. And from that, you can make a three-dimensional reconstruction of the subsurface. From a geologist's point of view, this is fantastic. It allows us to cover large areas of a planetary surface, even if you can't get down there. So we're very lucky in that we actually have 2 radars currently in orbit around Mars. So the first one, the one that was the study for the lake was based on, is the MARSIS instrument that's on board the European Space Agency's Mars Express. And the MARSIS can be seen as the large antenna that's basically coming out in front and back of the spacecraft and down below. And then we also have the NASA's Mars Reconnaissance Orbiter with the SHARAD radar, which also has this antenna showing, which I'm personally involved in as well. And so both of these radars are described as sounders, and what that means is they transmit very long wavelengths, meters to tens of meters. And the idea here is simply to get as deep as you can into the subsurface and really get an understanding of what the sort of crust of planetary bodies is made of. And what it's essentially doing is creating an X-ray of the ground view. So here we have a three-dimensional topographic model of the North Polar Cap of Mars. The warm colors means high elevation. And so what I'll give you an idea is, as the spacecraft fly over the top of this, it's trying to make a slice through that. And basically, if you just go through, you can start to peel away some of this, and you're left with this image that's looking sideways, basically straight down to ground. And as I said, kind of like an X-ray. So the top one here is a SHARAD image of the North Polar Cap. And there's lots of wonderful detail. You can see the outer shape of it, you can see internal structure, and you can see the base as well. Below it, you have MARSIS looking at the South Polar Cap. Now, obviously, there's a difference between these two images, and the reason is MARSIS transmits, multiple channels, but one of which is 60-meter-long wavelengths, and this allows it to see super deep into the subsurface. But the trade-off there is you lose resolution. So the MARSIS image, even though they're looking at 2 caps, there are some differences between them. The MARSIS image looks a bit coarser, but it's allowed to go much deeper. Whereas the SHARAD one can see much more detail, but it's only 15 meters wavelength, so it can't see quite the base of the southern polar cap as MARSIS. And that is why MARSIS has been employed in looking for lakes in this region. So before I explain how MARSIS was used to look for the lake on Mars, I want to explain how this is done on the Earth. Because basically, what scientists are doing in planetary science in a lot of cases is we're learning from our colleagues in the terrestrial sciences, looking at Earth and seeing their techniques and then trying to apply them to other planetary bodies. So we're going to look now here at possibly one of the best analogs for the Mars Lake, which is Devon Island. It's an island in the high Canadian Arctic. And there's this ice sheet, which you can see here. And a paper that was also released this year where they used radar, but instead of satellites like we do for Mars, they had the radar on their fastened to Twin Otter aircraft, and they flew over this ice sheet. And that panel on the top right, we can see is the red lines corresponding to every time they've flown over. And so what they're trying to do is fly over and make those same sort of like X-ray images I showed you of Mars. And so here in the top right, you can see the equivalent image there. And they try to do 2 things to look for lakes. The first one is that they try to look for the structure. And so we can see in that top right panel, the very top is the surface. It's not so clear here, but you'd see lots of lines in it, which is internal layering. You can see one very prominent line there, which is an internal layer. And then at the bottom, you can see that kind of undulating horizon, which is the base of the glacier as it's sitting on the original bedrock. And so what from that you can see is you can highlight areas where you have what appears to be valleys. So if you're going to get ice below the ice, you'd expect it to go into these valleys. The second thing they do is they look for the power return. So each echo that comes back, you can measure how strong it is. So to give you a sort of analogy of that, imagine yourself, the human body is kind of being a radar. Imagine you've been in a dark room, your eyes are the receiver, and you have a flashlight. As you've shined a flashlight on a wall, you can see that where it's illuminated. As you keep walking, if you went past the mirror, suddenly you'd almost be temporarily blinded by it coming back. And that's because your eye is receiving a lot more energy from the mirror than you are from the wall. And it just so happens when you get this buried water, it's a lot more reflective than, say, bedrock. And so what you're looking for is areas of high power. And this middle image here, it's showing where you have these two valleys. And what they're finding is the power is much stronger in these valleys. And so the two evidences together was leading them to suggest that this was, in fact, strong evidence that there have been lakes. Now, this ice sheet isn't as thick as Antarctica, and so what they invoked here was that was due to salt was allowed them to be liquid. Now, because it's on Earth, you've had geologists actually go to surface, old school, chip away at the rock, and this area has very old sediments. They're evaporites, which basically means they're very salt rich, and that would supply the salt to this region, allowing them to be these very super, briny waters. So how do they, basically for Mars, the same technique was applied. You took the radar flies over the polar caps and you look for lakes. Now, unfortunately for Mars, because it's such a long wavelength, it has quite coarse resolution, especially compared to an aircraft flying over Greenland. And so you don't get to see so much structure. So on the far right, you see the panel, you can see the sort of X-ray image they produced, the radargram as we call it. And so you couldn't see the sort of structure like valleys where you might look for water. But what you can still do is you can still apply look for the reflected strength as we saw of Greenland. And indeed, what they found is that certain areas of the base here had a really strong reflection, which they interpreted to be water. Now, to be fair, this paper is a lot more complicated than, oh, there we go, it's very, very bright, must be water. It's a very complicated process in which to sort of dial that back. And the reason is, Mars, just like Shroud, was designed to look for structure. It wasn't designed to measure specifically power. They weren't, as we would say, calibrated for this. It's challenging enough to get a radar into orbit, let alone send it to Mars. So, especially when you have these 20-meter-long antennas, which are tricky to deploy. And so, really, they had to deal with, one, an uncalibrated antenna, which means they're not exactly sure of the power it's outputted in every given time. And two, they have to deal with looking for these things under this really thick ice cap that's on another planet that we've never actually had, people on the surface going around. So to give you an analogy of kind of how complicated it is, go back to our room. You're in there and, it's come close to Halloween, so someone's put some dry ice on the ground, so it's kind of seeming very hazy and there, very misty. And what you're trying to look for is the difference between white patches and, say, a dark gray wall. And not only that, but your flashlight doesn't also give you a constant beam. Your flashlight is going brighter and darker, and you have no way of controlling that. As you're walking through the room, it's kind of confusing from one point to the next to say, oh, that looks brighter than the other. Is that because there's some white paint, or is that just because my flashlight was getting a bit brighter then? And it's the same thing that had to be done in this paper. So painstaking work was gone through to try the best to sort of tease out differences in power, try and best understand or model what the ice was like. And what they were able to produce is this middle panel here, which is their best interpretation of what the power return is. Now, right in the middle of that is blue, and that means high power. And so, yes, they got this high-powered signal once they've corrected for all these things that can affect the signal. And what's great is that each one of these lines is an individual track going across the surface of the polar cap. Now, what is really reassuring for these researchers is that as multiple times they crossed the same spot, it kept appearing to be bright. And so that led them to believe, yes, this is something real, there's something very bright below here, and the most logical explanation is water. Now, because Mars is much colder, the pressure on top of this area isn't enough, especially because it's not even under the thickest part of the cap, in order to cause liquid water. So they invoked that it could be salts. Well, of course, you don't have a geologist like you did in the high Canadian Arctic to look for the bedrock, tell you what it is. But we have robotic geologists on the surface, and the Phoenix Lander found evidence for large amounts of salts in the high Arctic. And so this idea that we could have abundance of salts in the subsurface, which would allow these hypersaline brines and allow this to exist. So it's a really compelling discovery. It's kind of in an interesting place. As I said, you maybe think it would be under the thickest part of the cap. And certainly maybe the jury's still out if this is exactly liquid water is the right answer. But what this gives us now is a place to target, to keep using MARSIS, to look for shroud. As I said before, shroud we don't think can see as deep. But if this really is water, maybe it's worth us going back to our data and seeing, can in the same area maybe tease out in the faintest echo, because if it is water, it should be bright. And so this is going to keep us busy for many years to come. But, very exciting. And of course, if it is water, maybe it has life. So with that, thanks very much.
All right, thanks a lot, Gareth. Now we're going to hear from Jennifer. Tell us about what's happening with the Mars rover.
Okay, so we're going to jump from physics to some chemistry. So I'm going to give you sort of the chemist's worldview about how we use the robotic assets on the surface of Mars to look for life. And I'm going to talk about, in specific, the Curiosity rover, and which is, I'm part of the rover team, and I'm also part of the Sample Analysis at Mars team, which is an instrument on the rover that we use to look for molecular evidence of life. And so what you see up here when we ask the question of could life have ever emerged on Mars? So there's actually a couple questions here. There's the search for extinct life, and there's the search for extant life, so life that would be living now. And you can use the same instruments, but you may look in different places and you may look for different signatures. But in general, we're looking for major biogenic elements, so the carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So all of the things that life uses to make biomolecules, and also to make the molecules that replicate information, such as DNA and RNA. We're also looking for potential sources of energy, whether they're present or past, and that could be something like sunlight, but it could also be chemical and thermal energy like you might find at an ancient hydrothermal vent. We're also, of course, we're interested in water as well, and water is the universal solvent. So water can bring all of these elements together, water can enhance the chemistry, and life as we know it requires liquid water. But even if you have all of these things, you may not necessarily get life. And of course, there's also all of the physical requirements for life, which include things like, you've probably heard of the whole sort of Goldilocks idea, where you have a habitable zone near a star where it's not too hot, not too cold, where you can maintain liquid water and have life. And so there are some physical characteristics, but I'm going to focus right now on how we've measured some of the chemical requirements for life using the Curiosity rover. Okay, so the primary goal of Curiosity, which launched in 2011, landed in 2012, and is still roving on the surface of Mars for over 6 years now. So the goal is to go to a local region on Mars that we've chosen based on basically orbital information about where water would have been in the past and our knowledge of the age of that location, and to assess that region as a potential habitat for life, both past and present. And so prior to Curiosity, we were really focused on following the water, and that's what the instrument payloads of the rovers were built to do. Curiosity, we're adding to that approach by adding to our capability in order to look for things like carbon, nitrogen, oxygen, hydrogen, all of these other elements, and how they come together into more complex molecular species that may be indicative of either life or even of what we call prebiotic chemistry, so chemistry that could possibly lead to life. And so a lot of thought, of course, goes into where we're going in the first place, because we can't just land anywhere and expect to find the same thing. Mars is actually quite different. Now that we've learned so much from orbiting assets, we know that that there are different parts of Mars, there are different surface expressions that are different ages. And so basically the whole landing site process is very, very rigorous and vigorous because you have a bunch of scientists in a room over several different meetings over 2 or 3 years, and everybody's got their favorite site and the reasons for going there. And it's, people are very passionate about this. And the site that was selected for Curiosity was selected, it was Gale Crater, and the middle, what you see, sort of that peak in the middle is informally known as Mount Sharp. So Gale Crater is over 3.8 billion years old. And what happened is basically we believe that the crater formed, and then there was an aqueous environment, so water in the crater, and then you have sedimentation, so building up those layers, filling up the crater with sedimentary layers. And then much later, the winds came and basically exhumed that mountain that you see in the middle. And so what you have is a whole stack of sedimentary layers. And this, for geologists, is like, the mother lode, because what you have is at the bottom, you have the oldest stuff, and at the top, you have the youngest stuff. So you have basically a history in those layers. And not only that, but we've chosen a location that, as you can see, if you look on the left here, you see clear evidence of water scouring here. And so this is something you might see if you fly over the Southwest. You may see evidence of water scour, and we can see that in many different places on Mars. But what we also know about this location is that we have layers of clay. And now clay, based on the mineralogy from Earth, we know clay forms in water. And not only water, but water that has been calm and standing for a certain amount of time. So that gives us an idea of that that you could have a lake that's sitting, calm water, for long periods of time, long enough to build up these layers. And then the other interesting aspect about this sedimentary geology is that we have, above the clay minerals, we have sulfates. So sulfates also form in water, but they form in more acidic waters, and they form in drier environments. So what it looks like, what we believe that we've accessed with this site, is basically an environmental evolution on Mars that we're capturing in the rock record. And so that was some of the primary reasons this site was selected. So again, this is a nice, beautiful panorama, or piece of a panoramic picture taken from once we landed in Gale Crater, and you can see the layers. And the other thing, the significance of this age, of this 3.8 billion years, is that this is when life evolved on Earth. And so if we go to Mars, which hasn't had plate tectonics, where, on Earth, we have very, very few rocks that are that old to study, because plate tectonics just basically puts them back into the Earth, melts them, and then we lose that record. But on Mars, we have this record because we don't have plate tectonics. So the idea is to go somewhere on Mars where you have an environment that was aqueous, so there's water there, and that you have layers that might preserve that information from the time on Earth when we know life evolved on Earth. So go to Mars, try to understand whether any biological information is captured in these layers where we know that water existed. And so what we have is a rover with 10 instruments. Each one has different levels of complexity, but it's quite a payload. Oops, not yet, okay. There's 17 cameras alone on Curiosity. We have lasers, we have drills, we have a robotic arm with drills, and not only that, we're able to drill and then basically take a sample and process it, so we can sieve it through different so that the material is different sizes, and then the instrument or the arm actually portions the material and puts it into the instruments that are in the body of the rover. And the instrument that was built at NASA Goddard, just sort of down the street from here in Maryland, is called SAM, which is Sample Analysis at Mars. And so most of the data that I'm going to talk about is from that instrument. And what that instrument is it's a mass spectrometer. So we're actually looking at molecules and identifying them by their mass, along with some other characteristics. And so we can look at the composition of both the atmosphere and of solid rock themselves, whether we scoop it or whether it's drilled and the rover arm delivers a powder to us. And so we call this evolved gas analysis when we're looking at a solid. And let's see if this works. Okay, good. So you have a sample, and you heat it. And heating that, you turn it into gas. The gas goes into the mass spectrometer, where basically it's ionized. So the particles are basically imparted a charge. And by that, we are able to basically, the particles actually break apart into smaller pieces, into fragments, and we're able to measure the masses of those fragments and then sort of piece back together what the original the original molecule was. And so this is a very powerful technique. It also can lead to a lot of, it's hard to interpret all the data because what you have is an oven basically, and you're basically taking Mars, putting it in your oven, heating it up, and you're doing chemistry, you're doing a reaction. So it can take a while to interpret exactly what we're doing when we're heating all of this stuff together. Now, something I'd like to point out, some of the stuff that we've learned, this should look familiar. This graphic was put out by NASA, I don't know, maybe 2 years ago, and it drove me nuts for a while because the point of it was to show that, yes, all of these things, oxygen, carbon, hydrogen, all these things are found in Mars soil, that we've either detected them through the kind of in situ mass spectrometry that I've described, or sometimes work on Mars meteorites have detected these things. But just because they're there doesn't mean there's life, and it also doesn't mean you could actually grow potatoes in it, right? Because these chemicals or these elements need to be there in a way that's available, chemically and biologically available. Just because you have carbon or nitrogen doesn't mean that it's in a form that can be used, that you could grow things in. The other thing that I felt was remiss to mention about this was that we've measured large amounts of perchlorate in the soils, and perchlorate is toxic. And in fact, it's a real problem when we heat up our samples. You have reactive chlorine and oxygen, and that reacts with the samples. And so it's actually not too hard to remediate on Earth. Perchlorate's extremely soluble, so you could technically wash it away, but there's not a whole lot of water on Mars. So it always got to me a little bit that they never talked about that in the movie. So that's there. And sure, maybe you could use it as a source of oxygen. Who knows? But what we found, and we found this in the Phoenix lander, and we found this from the results of Curiosity. And we also, when we go back and look at Viking data, we can look and find that they have measured organic molecules that are chlorinated. So they see the evidence of this chlorine, and the belief is that this chlorine is coming from the perchlorate. And because we've measured it with different instruments, different missions, different places on Mars, we believe it's fairly ubiquitous. So we think it's pretty much everywhere. Anyway, I always love to point that out. A couple of things that we do have, though, the things that we've discovered are that with the Sample Analysis at Mars instrument and the Curiosity rover that are interesting in terms of life, or what we call habitability, basically the ability for life to exist on a planet, is we have found fixed nitrogen in the form of nitrate. And nitrate is the form of nitrogen that is in your fertilizer. So this is a form of nitrogen that is chemically and biologically available. It can be taken up and used by biology right away. And it's there in abundance that is sort of like, the most dry, like the Atacama Desert and the dry valleys of Antarctica, and places that are very devoid of life on Earth. Although you'd be surprised, anywhere you go on Earth, you pick up a handful of soil, and there's probably going to be a little bit of life in it. Which makes it really tough to actually study areas on Earth where there is no life, because you can't get away from it. So the amount of nitrogen that is on Mars theoretically is enough to sustain life. The other thing that's interesting that we find, and we don't find this using the SAM instrument, but we've measured phosphorus also in rocks on Mars. And so when you say, okay, you have phosphorus and you have nitrogen, those are major components or important parts of DNA and RNA. So if we are considering amino acids, things like proteins, life, any life that uses those sorts of things, or RNA or DNA, it's important to note that we do find these things on Mars. We do find these ingredients to life as we know it, and that some of them are actually chemically and biologically available. A recent discovery and a recent report earlier this summer was that of complex organic molecules on Mars. And so this is a tricky thing to interpret, because what we find is that complex organics don't necessarily mean that this is an organism that's broken down. Like often in the rock record on Earth, complex organics come from biology that has been degraded over time. But it can also come from meteorites. It can also come from non-biological sources and simply basically diagenesis, which is basically the way that rocks change over time and sort of chemical molecular changes over time. But it's quite exciting that in these 3.5 or 3.8 billion year old rocks, we find evidence of complex organic matter containing carbon and sulfur. So whether this was potential food for life, whether this was some possible remnant of life, or even if it came from meteorites, it's interesting because it means that we have a record in these ancient rocks. A lot of folks think that it's really hard to find organics in the surface of Mars because you have a lot of radiation. The surface is not a great place to be. So you have lots of radiation raining down. It's a very oxidizing environment. And so I think one of the most exciting things about this discovery is that, yes, these organics have been sitting there being bombarded with radiation, and yet, we still have a record of them. So just imagine if you go deeper, if you drill deeper, and the ExoMars rover will have a 2-meter drill. So the idea is to get down below the surface to where we might have, more organic molecules that have not been irradiated. So that's very exciting to know that, not only might we find them down there where they're protected, but we've actually measured them now from in-surface rocks. So a little bit more on, should be a little movie, okay. All right, so this is sort of how these molecules, what's detected are small pieces of a larger molecule. And so this is, kerogen is a complex organic on Earth, but what happens is it gets broken down over time into small pieces. And that's what we're detecting are the smaller pieces. We don't have a good idea of what the original structure was, but we're detecting small pieces of something that was highly likely much larger. And then finally, some of the exciting follow-up to this story of methane on Mars, which was reported in the 2000s initially from both ground-based and orbital measurements. And not only was methane detected, but the key point is that changes in the methane in the Mars atmosphere were detected. And so these changes are thought to be, they could be geological or they could be biological. And so the most recent information that we've gotten from Curiosity rover, as we've sat on the surface, measured, now we've been there, I think, for 2 Mars years. And so 1 Mars year is 2 Earth years. So we've got data compiled over time for, I think, about 2 Mars years, and we're still, we don't, there's a lot that goes into when we take a sample because everybody's competing to make a measurement. But what we have, at least, is enough information to show what looks like a potential seasonal cycle, right? So, and this is exciting because on Earth, most methane comes from biology. It comes from the breakdown of biological material by microbes. So, and as you can see, for example, cows do this in their stomach and contribute to methane to greenhouse gases. And so the fact that you have a seasonal change, this is highly interesting because we see seasonal changes on Earth based on basically how life responds to seasons. So this question's still outstanding as to whether we have a biological source of methane or something geological, because water interacting with rock can also create this. However, you'd have to figure out how that would be seasonal. We've also seen sort of spikes of methane. So we've seen higher values just randomly. So maybe it's a plume. No, we don't know. We sort of passed that spot where we saw it with the rover. We saw it once. We can't explain it. Was it released from something underground? But the question is, where did it come from? And also, where did it go? Because methane can be actually created by biology, but it's also consumed by biology. So it's a really interesting mystery that we continue to basically try to add data to explore. And I think that's it, actually. I'll end with that.
All right. Wonderful. Thank you, Jennifer. And now we have Michael.
So let's see. Figure out how to drive this. There we go. So what I want to do is do a little, where are we with Mars exploration? Tell you where we're going, kind of where we're standing. And I think it was interesting when Dave was talking, it occurred to me that when Viking landed on Mars and did measurements and basically showing that Mars was dead, is at the same time, we had oceanographers looking at hydrothermal vents and suddenly realizing that they're alive. And this really did launch the whole aspect of looking for life in extreme environments. And as that science progressed, it came to the realization that, here on this planet, despite all we thought we knew about life, all you need to do is find out where liquid water is, and then there is that potential for life. You find it in hydrothermal vents, you find it in extreme places in deserts, and it sort of put a new light on what we're doing at Mars, in that we didn't find life on the surface of Mars because there's no water on the surface of Mars. So what we should be doing is looking where water is or was on Mars, and maybe it has life. So that concept actually has fueled modern Mars exploration. And this graphic up here shows the series of missions that we've had that interplayed with each other, of looking at Mars from orbit, then sending something down onto the surface to confirm what we think we're seeing from orbit, or actually surprise us of seeing things that we didn't see from orbit. And it's been a real process of discovery, of leapfrogging between the surface and an orbit as we go further and explore Mars. And the real question is, as Jen mentioned, is like, follow the water. We should be, follow the water. If we find water, then you have the potential for life. And that has actually progressed in that, well, not only have we found evidence of water in the past, and as we've seen with Gareth's talk, in the present, it points to, okay, now we have places that have the potential for life. What do we know about it? As you heard from Jen, we found at least one habitat in Gale Crater where all the ingredients that we know are required for life have been found and represent that in Gale Crater's past, it was a habitable environment. So of course the question is, did life ever get started there? So Mars has proved to be a place where the question to ask of whether or not life ever got started there is still an extremely valid question. And because of that, we now have several spacefaring nations wanting to send their spacecraft to Mars and go through the exploration. And if you look in 2018, InSight's going to land the day after Thanksgiving. I'll measure the geophysics, see whether or not Mars is alive in terms of Marsquakes. But in 2020, there's going to be a series of orbiters. We're sending 2 landers to, or part of one, ExoMars, and we're sending another lander, Mars 2020, to explore the surface of Mars. The Chinese have mentioned going to Mars and not only sending an orbiter, but also sending something on the surface to collect samples and have a sample return. So things are happening on Mars, and it's starting. In fact, it's going to start getting crowded. And it's because the concept that Mars has proven to be a place that still has that biological potential. And I just put this up here is with a background of Murray Butts, that a lot of really good science is coming out of planetary sciences, of understanding how planets work, what its past was, how things happen, being in the forefront of science, and for fun, in the bottom left-hand corner, I put an astronaut there for scale. So what's happening on Mars today? Well, right now, we're just concluding a dust storm. I think it's impressive where this is a model of the amount of light reaching the surface of where opportunity is when the dust storm, global encircling dust event occurred. And in the bottom left, there's a graph. I'm not sure if you can see it, but the red line is the amount of light that's transmitted through the atmosphere onto the surface of Mars, and the dark line is a measure of atmospheric opacity, which is called tau. So tau at this time of year on Mars hovers around 1, 1.5, something like that. And you can see the amount of light that gets to the surface, and then basically in early June, the amount of light reaching the surface plummets, the tau rockets up. The highest we were able to measure with opportunity was 10.8, and this is a logarithmic scale, 10.8, and then we didn't hear from the rover again because it doesn't have enough power to talk to us. Dust storm's over. Hopefully the solar panels are recharging, but there may be dust on the solar panels left from the storm, and so we still haven't heard anything from Opportunity. But the point is, dust storms are real, and it's a problem. May not be the same problem that Matt Damon encountered, but it can be a problem. One of the things is finding ice in places where we didn't expect it. Models tell us that there ought to be ice stable in the near subsurface and basically in the blue area of that map of Mars. But because of crater impacts, meteorite impacts forming craters, we can see subsurface ice in areas where it shouldn't be stable. As we see, we found subsurface lake in the south polar layer terrain. And as Jen mentioned, we're finding complex organic compounds. So the point of highlighting these things is that not only does Mars have evidence of liquid water, it has places where water we didn't expect it in the form of ice in the mid-latitudes. We have complex organic compounds in the actually almost equatorial areas of Mars. So there's something to look at. There's a record there. Right now, it's too complex for us to sort out the type of instruments that we're sending. We can't remove the perchlorate that may be knackering the complex compounds we're trying to study. So there's lots to learn. And then there's methane, a phenomenon we cannot explain. We see a seasonal cycle, and then once in a while, some of the instruments show a burst. We found it on the surface of Mars. We've also seen it from Earth looking at Mars, a very complex measurement, and it's impressive. It's a real mystery. So let me go into what we're going in the future. I know we're running out of time. I want to hear questions. InSight's going to land November 26th, and it has two major instruments. One that will measure the seismicity, will measure whether or not there's Mars quakes, and also will measure the heat flux from the surface. And so that gives us an idea of how fast Mars is actually losing heat. In 2020, as I mentioned, two rovers are going, one by ESA, in which we have a major instrument called MOMA on it, which is going to measure organic compounds, and us actually use a different instrument to extract complex compounds that are stuck on surfaces that we can't find other ways. And then also NASA is sending Mars 2020, which has a complex set of instruments that can tell us where organic compounds are and the interrelationships between grains, when you look really close into the surface. The thing that I find going to be very interesting about the Mars 2020 is that it has the capability to see organics if there happens to be finding a good deposit of them. We know that there's organics there, but the problem is they're very few and dispersed, and it's hard to get a good measurement when you have so few compounds to measure. But the real thing is, it's going to cache a sample. So let me see. It is, oh, there we go. So this is obviously a model, and it's going to cache samples, get a core, drilling a rock, and then put it in a tube and deposit on the surface, and then some other mission is going to come and get those tubes and bring them back to Earth. Now, it could be Chinese are going to do that, or we have the opportunity to do that. We'll see what happens. So this year, we got money from Congress, permission to study doing sample return. We have one mission on the books that's going to launch in 2020 that will cache samples and leave them on the surface, and now we have the opportunity to study how feasible it is for us to send a mission and go and get those tubes and bring them back to Earth. The importance of this is now you can look at Mars on a grain-by-grain basis. You can do experiments in the lab. You can manipulate all your samples and do every single measurement you could ever think of with the most sophisticated instrumentation on the planet. And that's going to tell us something about the history of Mars and its biological potential. And I'm wondering where the label was. Anyway, I just thought this was a cool picture, and it will be the first opportunity for us to bring a sample back from another planet. Interesting enough, we had a Mars sample return conference, the second one in actually a decade, in Berlin this April. And basically one of the questions we asked is, what do you think, what do you hope to answer with the Mars sample return? And this is one of those Mentimeter, which basically, depending upon how many people mention a certain word, it gets bigger in the diagram. And it just shows you that life is foremost in terms of what we think we might be able to answer by bringing samples back. And with that, I'll just leave it. And I think now, David, we can be a panel now.
Yeah, absolutely. Thank you, Michael. What a terrific set of talks. You know, all different, and yet all on the same topic. It's such a rich topic. And now we have a little bit of time for discussion and questions. So please raise your hands if you've got a question, and you can address it to an individual panelist, or just throw out the question and see who wants to bite. Yes, sir.
Hi, I didn't get everyone's last name on the panel.
Oh, we can do that again. Gareth Morgan. Jennifer Stern, Michael Myers, and
No, there's only one of me.
oh, sorry, Michael Meyer. Actually, there's 3 Michael Myers, but you're only one of them.
Yeah.
Okay, thanks. Well, Dr. Jennifer
Stern.
Stern.
Yeah. Yep.
Right. You had a slide that reminded me, about the what we consider the essential elements for life, which NOx, carbon, hydrogen, oxygen, and phosphorus, and sulfur. But I had the opportunity 25 years ago to run a simulation, kind of like the O'Barron and the Stanley Miller and Curie experiments.
Sure.
And what I wound up noticing was that, including some of those elements, but with the exclusion of phosphorus and sulfur, although I admit I'm not be up to date. But what would you all say now about when and how those other elements would be included in such, what you think, central kind of experiments to astrobiology?
Oh, you were asked that question.
So I guess I would answer or attempt to answer by saying I think a good starting place is looking at things like meteorites and that the fact that they contain things like amino acids. Basically, looking at the inventory of those things in meteorites, and by that way we get an idea of what was available. Basically, what stuff, what elements and what molecules might have been available for life to use, because that's probably what life on Earth started with. And so I would think that at least Mars and Earth being close and being basically experiencing the same early solar system history as meteorites, basically Mars, meteorites, and Earth, are all very similar in a lot of ways. And the fact that we see things like amino acids and nucleic acids, nucleobases in meteorites, probably tells us that at least carbon, nitrogen, hydrogen, oxygen are probably important. You know, we know that at least for RNA and DNA-based life, that phosphorus is also important in there, and sulfur is also important in a lot of enzymes. So it's hard to say. It's really hard to say. I mean, the first thing we sort of do with habitability is look at what's available. And I have not done a lot of things like simulations to understand sort of which elements would be more or less compatible with different environments.
And I might be able to offer a slightly different take, in that I think the real import of that Miller-Urey experiment is it demonstrated that you can go from elements, simple compounds, in a plausible scenario of what might have been like on early Earth, and generate what's considered biogenic compounds. You can generate the amino acids. And what that does was sort of a realization that you can get something that's biologically important from an abiotic process. And that, I think that was the key to that experiment. It is not necessarily the way that those things were made, right? So there's lots of other ways to make organic compounds on early Earth that doesn't require lightning in an atmosphere. And so it's a proof of concept that you can get from step 1 to step 2. It doesn't necessarily say that's what the step was. It just shows that it's possible. So.
Other questions? Hands? In the back. Sure.
Okay.
This is with regards to Mars 2020. Have they decided on the landing mechanism? Are they going to use the sky crane again? And with regards to the little geocaching thing, have you guys thought about legally who owns those? Like, are we going to
Interesting thought.
Yeah.
Yeah, so just to repeat the question, Mars 2020, how's it going to land? Is it going to be similar to the scary 7 Minutes of Terror of the MSL? And are there legal questions about the cached samples? Has anybody thought about who owns them?
Right. So answer to question 1, that one, we know that one. So we're going to use basically the same mechanism as Sky Crane. And in fact, if you look at pictures of Curiosity versus pictures of the 2020 rover, they look pretty much the same. And in fact, the way you can tell the differences is whether or not it has zigzag patterns on the wheel, which is Curiosity, or straight bars across the wheel, and that's on 2020. So that was one of the improvements after learning that you can't go across sharp rocks very easily with the rover. Legally, anybody can go and pick those up. They're not ours. We've foregone property rights in space exploration. That's part of the Space Treaty of 1967. That it's open. It's like open seas. It's sort of just like in the ocean. You can go pick up anything you want outside of national territories or continental shelf. And in fact, that's been very beneficial. You have freedom in the open seas and that sort of thing. There is, in some ways, a natural consequence. One of the, let's say if you find something extremely interesting in the open ocean that you would like to go mine, you may not want to do that, because if you find something really good and you start making money, everybody else can show up because you don't have rights to it. So you'd be in competition with anybody else. So that the other side of it is, because there's no property rights, it also means that anybody else can go and pick up your cash.
Oh, it'd be great if somebody went and brought them back as long as they share the science with
Right.
us.
Yeah, well, yeah, as long as,
Yeah.
right? But you do have to worry about what, some commercial ventures may not have the same attitude.
Or they want to
so.
sell them to us. Yeah. Let's see. Yes, right here.
So are there any of the rovers and any of the tools that are on Streets to Mars right now, are any of them specifically looking for like fossilized cyanobacteria like stromatolites? And would they be recognizing if they saw it, or would they just be looking at like chemical traces?
So the question is, are any of the specific tools on Mars right now looking for fossilized cyanobacteria like stromatolites, and would they be able to recognize them if they found them?
So that's a good question. I can answer for curiosity, and if you want, you can answer for 2020 stuff. But certainly, I mean, we have MALI, which is basically a hand lens imager, so we could see things like the bands. I mean, we might be able to see some of those things. And if you combine some of that morphological information then with detecting, certain molecular biosignatures, because we can see things like hydrocarbons, fatty acids, amino acids, that sort of thing. So if you had, the first question is, are those things preserved on the surface? And that's one of the hard questions is that, they would have to survive, or the biosignatures would have to survive over the 3.5 or whatever billions of years. But if they're there, we should be able to detect the molecular fragments and also things like, we can detect what's in the layers. We have ChemCam, which is basically a laser ionization breakdown spectroscopy. So you can shoot a laser at this very small spot, and then looking at basically the wavelength of the plasma that's emanated, we can get an idea of the chemistry. We also have APXS, so we could see, okay, is there iron here? Magnesium. So we could, if the information is there, we could probably use the combination of the visual morphological information, the sort of elemental geochemistry, and then also that molecular information, if it's all there. So theoretically, if it's preserved, we should, with curiosity, be able to see something like that.
I mean, if there was actually a stromatolite, even the cameras might clue us in.
Right,
Yeah.
right.
So in contrast, so on Curiosity, it can measure what's there and tell you whether or not there's organic compounds, and it can tell you what elements are there. It might be able to see some morphological features, but because the way it measures things, it destroys what it's measuring and does it in bulk. So it's like you put it into it. You pour everything in a test tube, do your chemical reaction, go yahoo! Here's what chemicals we found. In contrast to it, because 2020 is geared toward let's find some really good samples, cache them so we can bring them back. What's on board 2020 is the ability to look on a microscopic level of distribution of elements. So there's an instrument called Pixel. It can tell you the distribution of elements. So it could tell you if there's one element always next to another one in terms of a mineral assemblage. And so that can be very interesting. That can tell you whether or not there's a battery there where you have an oxidized and reduced species and would be a chemical potential for life to take advantage of. And then the other instrument called Sherlock, it uses a UV light, it's Raman spectroscopy, and what it can do is it can highlight if there's certain minerals, including organic compounds. So now you can see organic compounds in association with certain minerals, and then you go, okay, now this is really interesting. It's not going to tell you if you just found life, though. The scale of it is not still close enough. But it'll tell you that sample is really interesting. You're going to cache it, and then we will have to race other spacefaring entities there to go pick it up because everybody would want to have that brass ring.
There was in the corner here, and then we'll get to you. Yeah.
Forgive me, but I may be Chinese literature. It's somewhat distant from the topic of discussion. But my understanding, so I'll iterate my understanding to make sure it's relatively accurate and then pose a question space. My understanding is you said that complex organic compounds are going to be rare, closer to the surface of Mars on account of essentially bombarded by radiation. Is this correct? Okay, good. So given that,
So ExoMars, which is the European Space Agency's lander, they will have a 2-meter drill. And while they're not taking, I don't think they're not taking cores. They're going to drill and they'll have powder. Is that correct? Or are they taking cores?
No, it's powder because they're
Yeah.
putting it into their sampling drawer.
Right. So they will be getting below that layer, and the drill was designed to get below, so that like between models and experiments, they think that 2 meters is sort of the 1 to 2 meters is sort of the sweet spot to get down there. But the great thing about Curiosity is that we've just seen at least that these things can be preserved on the surface based on the chemistry. And in the case of some of this data, it was because the way that the carbon and the sulfur were interacting with each other, the sulfur actually kind of stabilized the carbon. But yeah, and there's a lot of development that goes on in terms of what we do on Earth. When we go to a Mars-like environment on Earth, there's a lot of testing of coring and drilling equipment because it can be hard on Earth to do, and it's even tougher on Mars to get that stuff to work. So that stuff is definitely in development.
Okay, over here.
I was just going to say, I know that early on in concepts for 2020, the idea of taking your core and laying it out so you can look at it and see what the difference is between the bottom and the top, it was just decided there's no way we can do that and everything else that we want to do. And so now the only hope of finding out, and the problem with 2020, it's only going to go down 10 centimeters or so. They'll be able to use the instruments to kind of look into the hole to see if there's something interesting beyond what you see from the surface.
But it's a great idea. I mean, even though we're telling you all these impressive accomplishments, historically, Mars exploration is probably really still at its beginning. Yeah. And that's something that probably ought to be done at some point.
So two questions, one for Gareth and Michael, and another one for all panelists. One, I got to catch up to what I was going to say, because so interesting what you're saying. My gosh. Okay, so with the work that you're doing, Michael and Gareth, will any of that help advance our understanding of the interior of Mars at some point, where we can detect whether or not there are lava tubes and such? And also, second question is with this lunar activity that we're going to see in the next decade or so, is there anything you're looking forward to in terms of science done to the lunar surface or in orbit that will help advance some of the science that we've done on Mars?
In terms of lava tubes, I mean, we pretty confident they're on Mars because we see what's called like skylights, these little pits, and they're not like impact craters. You can see they go down and into a void. And when you look at the camera from different angles, from space, different times of day, you can see the shadow moving around. You can see it's a tube. And Mars has a lot of relatively young volcanics, the basaltic, like you see in Hawaii and Iceland, and so lava tubes are expected to be there. In terms of detecting them by radar, the Japanese sounder that was in orbit around the moon actually had a paper out, I believe, last year, which they claimed that they were using a sounder to spot them. It's very tricky because you're at the very sort of maximum resolution. So instead of actually, I've shown those kind of like almost like X-ray images, you're looking at individual pulses and trying to look for response. And I have colleagues on the SHARAD team that are currently trying to do the same thing. And so far, there's some indications we might do, but it's definitely work in progress. But yeah, in terms of using the moon, I mean, from a volcanic standpoint, the lunar mare, the parts of the moon, the face of the moon that looks darker than the rest of it, that's all from basaltic flood basalts. And so it shares a lot of similarities with what we see in places like Lys and Plessia or, Tharsis on Mars. There's definitely stuff we can learn between the two.
Okay, I guess why I asked the question is because you're talking about all the layers that are being detected on just the surface.
Mm-hmm.
Obviously, you can see some type of gap in between the layers that may indicate some site for space.
We could do, yeah. I mean, if you had the sort of rover on the surface, you could definitely see that quite easily. And from space, you said it's just a case of the resolution. When you're that far high up, you really do have a large footprint, so it gets much trickier. But certainly, I mean, that's the point of radar design to do that.
Yeah, and also, correct me if I'm wrong, but with the radars that we've had flying over Mars now, basically the top 10 meters, it's extremely difficult to resolve anything because of clutter. So, and what you'd be interested in terms of lava tube is up near that surface. That makes it a real problem.
Yeah.
2020 is going to have a ground penetrating radar. And so if there is something like a lava tube near the surface, but you don't see any surface expression of it, you may be able to see it with the ground penetrating radar.
Yeah.
Yeah, you had to rove right over it.
Actually, ExoMars also has the GPR as well.
Oh, yeah, that's right.
Yeah,
Yeah.
there's going to be 2 sent to Mars. We're quite excited to see what they can find.
By the way, those lava tubes might come in real handy when people go to try to live on Mars, because one of the hazards there is that when there's some extreme solar activity, you can get cooked if you're on the surface, and the best way to deal with that is to have a shelter where you can get underground for a while and be under some layer of rock. That's the best way to protect against that. So if there's a natural cave structure underground, then that could really help.
Well, that MIT, I think it was MIT, I think they came out where students looking at data from, I forget which mission it was, I don't think it was Colorado, and showing, basically comparing lava tubes here on Earth and lava tubes on the moon, and showing how big these monsters can be, and they showed downtown Philadelphia in like a corner of one. Actually, I think it's a good visual because you do think about habitation on the lunar surface right underneath Mars. I think that everyone in their minds thinks of something different. Some people probably think it's like as cramped as a submarine. You know, people may think it's of the size, but
It's also beneficial in that galactic cosmic rays is something that you can't escape. And the only thing that reduces galactic cosmic rays is mass. And so being under several meters of regolith is a big help. Right.
Yeah. Other questions? Oh, over here.
Yeah, I wonder if you could talk a little bit about the relative likelihood. You're obviously, we're looking for life on Mars. Are there other places, for example, Europa, that are equally likely? Obviously, probably not more likely to be looking there, but do astrobiologists tend to strongly think it's Mars, or are we just checking there because it's easy?
Yeah, so the question, to repeat for anyone listening, was about other places in the solar system, and what do astrobiologists think of the relative likelihood of, say, Europa or other places compared to Mars. Just a general comment, because we only have one example of a planet with life, we have a lot of ideas that, we think are grounded to some degree on what we've learned about life on Earth and what we've learned about other environments, but it's all somewhat speculative. So I think we all have a sense that it's smart to explore kind of broadly and not be really fixed on just one place. So Mars is promising for some of the reasons we've talked about. I mean, I think it's widely believed among astrobiologists that Mars should have had life, given what we know about the conditions for origin of life on Earth and the early conditions of Mars. So at least finding fossil signs of life seems very credible. You'll find a much wider divergence of opinions about whether there's life on Mars today, but I think you'll find very few astrobiologists who say it's not worth looking. Even people that are skeptical think, well, yeah, we got to go look. Europa is a very different kind of place. We don't think so much about finding fossils of ancient life there, but because there's it seems to be an ocean, and an ocean with energy flows and probably organics, there's great potential for life today, and yet a less Earth-like kind of life, not life that's ever lived on a surface of a planet with an atmosphere. So there's sort of pros and cons, and you can check them off. You can talk about Enceladus, you can even talk about Titan. But I think in general, astrobiologists will say, well, we really need to explore all these places because it's foolish to have a very specific idea when we have the proper humility that we're still kind of stabbing in the dark, hopefully in an educated way.
And just to add to that, we know that there's life on this planet, and there's wide-ranging and vociferous debate about where life started on this planet. So we don't even know how it got started here. It's a little bit of a hubris to try and guess exactly where it might have started somewhere else.
I will say then the nice thing about Mars is that it is close enough that we've been able to iterate. And each time we go there, we learn more, not only about the environment, but about how our instruments work in the environment. So it's been a great opportunity to sort of improve upon what we've done the previous time, each time we go. Now, a mission to Europa, we might only get 1 or 2 in our lifetime. So that's a totally different beast. So it's really interesting the way that you, to me, as somebody who works on developing instruments and mission concepts, is really interesting to sort of think of how do you approach those 2 different problems.
Okay, we're running short on time, but we have time for one more question. So we have one hand up. So.
Okay, I have a quick comment and a question. I will keep this brief. I tend to be a critical optimist. And when you were speaking, I was reminded that actually, and I had to look up his name, Giovanni Scarpelli, the Italian, who first, during 1877 opposition of Mars, observed what he described in Italian as canali, which later got arguably mistranslated instead of channels into canals.
Right.
Got the English-speaking scientific world all excited, very much like what happens today on social media. Everybody's thinking, oh, he's talking about canals, they must therefore be made by intelligent life rather than something through a natural process. Given that we're seeing these radar returns from underneath the ice, you didn't really speak very much to what extent that may be from something other than liquid water, mineral formations. What is the likelihood of that? What are the other considerations there?
So just very quickly, there was a comment that Schiaparelli, who first observed what came to be called the canals, used the Italian word canali, which just actually meant channels, and then that turned into canals. So interesting comment there. And then the question was about.
What other interpretations could there be for the high power return?
Yeah. So how definitive is the determination of the underground lakes as opposed to other possible signals that you might be getting?
Right, so then you're trying to get a value for the power, and then we know liquid water would have a certain power value returned. In order to do that, you have to make some assumptions about what the ice is above it and the temperature of the ice as well, and its composition. Now, the authors did a really good job of really trying to constrain that with the best of our knowledge, and which gave us the power return that matches water. But there is potential that there could be something different about that particular area, whether it be on the surface. It's worth noticing as well that in order to sort of understand the subsurface return, we normally normalize that to the surface return because that gets rid of a lot of uncertainties. Now, when we're talking about the surface, we're used to looking at images of Mars, but when we're looking at a radar that's got a 60-meter wavelength, that surface is quite thick. So they went through the other data sets and they didn't see anything abnormal about that surface. But that doesn't mean to say that maybe there's something is. And what we're seeing is that something's causing that signal, but it could be that's maybe within the column itself. And so that is why, further testing will go on. But in terms of the assumption they made was the best of the knowledge we have. So it's by far the best interpretation of that. But there still could be some uncertainties.
I was curious as to what other options were explored, whether there could be mineralogical formation, even metal-containing formations underneath that ice.
Well, it's more a case the column of the ice. They could be there's difference in temperatures, or it could be that there's CO2. Now, we know the CO2 on the top, and interestingly, other radar returns have found that there'd be large pockets of CO2 in the South Polar Cap. So maybe there's some pockets of CO2 along there as well, which has also changed the way the radiation would propagate. So that could be along the line. There's mainly something about the whole column itself. But you're right, maybe there is something anomalous at the bottom as well, but it's more likely to be in the ice.
Could it be a giant black obelisk?
No.
Yeah.
No. Where all the Martians decided to bury their tinfoil hats.
Yeah, many possibilities, but we tend to, using Occam's razor, we'll ignore most of them. But at any rate, we have to bring this evening's program to a close. Thank you all for the wonderful presentations, and thank you all for the wonderful questions and discussions. And the good news is we're going to keep exploring. There are more missions coming up. There are going to be more results. And so stay tuned, and we'll have to gather again in a few years and tell you all the wonderful new results we have. So thank you very much.
So So thank you so much, everyone, for coming tonight. I hope you enjoyed that as much as I did. You know, I think it's really a privilege that we can all come here tonight and hear directly from the people that are making some of the greatest discoveries of our generation and maybe even of our civilization. So I would really like to see you all talk again in May at Escape Velocity, maybe with enough round of applause a second time. We can just make everybody feel really appreciated and excited about coming back. So just one more time for me, please. And of course, I'd like to see all of you at Escape Velocity. And if you have a desire to get involved and share in our mission, please let us know and join as a volunteer and help us bring more programming like this to the general public. Thank you so much.
So last time I saw you was at 60 Minutes in Space.